in this video, we are going to talk about bitwise operations. Let's start with not. Okay. So in not, the thing is really easy. The input bit is inversed. That's all. So let's say you have not one. Okay. Not one means that is equals to zero. Why? You're just converting the ones into zeros. And let's say you have not zero, well then the output will be 1. That's all. Let's say you have not 101, well then the output will be 010. That's it. Okay, sometimes they may even mention it's a 4-bit system or 6-bit system. I mean, not a 6-bit system, obviously, 4-bit system or 8-bit system, like that. Okay, let's say we have a 4-bit system that states 0101. Okay, well then not 0101 will be 1010. Okay, you may think this 0 carries no value, right? You may think like that, but the system uses 4 bits, so it looks like this. Okay, you have to do it like this. Okay, so let's continue. Let's say we have not 010010 11. Well, this is a 8-bit system. Okay, so what will be the output? 10110100. Okay, and similarly, let's say we have not 00010100. Well, what will be the output? The output will be 11101011. Okay, so these are some examples that you can do. Okay, what about decimal numbers? What if we have something like not 11? What should we do now? Well, in this case, okay, they are saying the 11 is in decimals system. Okay, so not 11 to the base 10. How can we do this? First of all, what you have to do is you have to convert it to binary system. Okay, but you can't just convert it to binary. You have to look for which system of binary representation we are using. Sometimes they may say this is in ASCII, sometimes they may say it's in BCD, or sometimes they might just say it just uses 4-bit system. Okay, so if it is using a 4-bit system, that means we can represent from 0 to 15. Since this is 11, okay, we can convert it to binary. How can we convert it? Well, 8, okay, no, 4, yeah, there is 2, there is 1. Well, this is the binary representation. So what will be the output? The output will be 0100. It's just a 4-bit system. They didn't talk about anything else. It's just a 4-bit system. Okay. What about if we have an 8-bit system? Something like this. 10101010. Okay. So if it's an 8-bit system, okay, well then the output will be 01010101. You can't remove this 0. Why? It's an 8-bit system. You have to use 8 bits, whether you like it or not. Okay. So why do I focus more on 8-bit system? Sometimes they may say the system is using 8 bits 2's complement representation. Well, then the story is a little bit different. Okay, so let's say they are asking us to find not 97 to the base 10. Okay, and they are saying the calculator or the computer uses 2's complement 8-bit system. So what you have to do is, first of all, you have to represent 97 to the base 10 in 2's complement 8-bit system. Okay, so 97 to the base 10 can be given as, since this is a positive number, the first bit will be 0, and 97 means we have 64, 96, there is no other bits, so we just need 1. Okay, so now it's good. Now we have to write this down in the 2's complement form. So it will be 0, 1, 1, 0, 0, 0, 0, 1. Okay, so there are 8 bits, perfect. Now what we have to do is we have to just do the not function. Okay, so if you do the not operation, what will be the output? It will be 1001. Yeah, 1110. Okay, you can't just give it in the decimal here. Okay, if you do that, that will be a huge mistake. Why is it a huge mistake? Because they said clearly this system, this computer or calculator or this machine uses 2's complement 8-bit system. Okay, which means if the first bit is in 1, okay, if the first bit is 1, that means it's a negative number. Okay, so what you have to do is you have to convert it to 1's complement first. So 01100001. Now you have to add 1 to this. If you add 1 to this, what will you get? You will get 0, 1, 1, 0, 0, 0, 1, 0. What is it equals to? Well, this is a positive number. Okay, positive. 64 plus 32, 96. 96 plus 2, 98. But this is not the answer. The answer is this guy. So it will be minus 98. Okay, so what's the answer for not 97 to the base 10? Well, it will be negative 98 to the base 10. Okay, so keep this in mind. Okay, because fortunately or unfortunately, Python uses this method. Okay, Python uses this method when it comes to bitwise operation. So this is very important. Okay, let's say we have not something like 78 to the base 10. Well, first of all, convert it to, the ones complement representation. So 78 is a positive number. So 0, 64, no 32, no 16. That is a 8. So it will be 72, 76, 78, no 1. Okay. And if you convert it back, it will be 1, 0, 1, 1, 0, 0, 0, 1. It's like ones complement. Okay. Now, since the first bit is negative, okay, you have to find the ones complement again. So the ones complement will be 0, 1, 0, 0, 1, 1, 1, 0. You have to add 1 to this. If you add 1 to this, you will get 0, 1, 0, 0, 1, 1, 1, 1. So this is equals to 79. Okay. So that means this is equals to minus 79. Okay. So not 79 to the base 10 will be equals to 78 to the base 10 will be equals to negative 79. Okay, keep this in mind when you're doing the question. Now, what you have to try is try a negative number. Okay, something like negative 91. Okay, try this, not negative 91 to the base 10. Try it and let me know the answer in the comments. Yeah. Okay, now let's talk about and. Okay, now let's talk about and. And is a little bit different from not, because in not you just had one input bit. Okay, but here you need two input bits. Okay, so what this means is you have a logic table. Okay, actually, there is a table for that. Okay, in that table we have four rows. Okay, four rows. So let's say we have the bit A, and let's say we have the bit B. So and can be represented as A dot B. Okay, A dot B. So it's pretty straightforward. The thing is you have 0, 1, 0, 1. Since there are two bits, you know this pattern. I have introduced you this method of writing down in the last video. I'll attach the link. 0, 0, 1, 1. Okay, so A dot B means you just have to multiply these things. So we know 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, and 1 into 1 is 1. Okay, this will be a very important thing in logic gates also, which fortunately we will be starting from tomorrow. Okay, but if you have any doubts, just keep this in mind that this is how AND works. Okay, so they will give you two numbers, like let's say they are giving 1, 0, 1, 0, and 1, 0, 0, 0. The output will be, how you can find this, you have to write down them in a vertical format. Okay, so 1, 0, 1, 0, 1, 0, 0, 0. Okay, so now you can find out the output. 0 into 0 is 0, 0 into 1 is 0, 0 into 0 is 0, 1 into 1 is 1. So the output will be 1, 0, 0, 0. Okay, so that's the important thing. When you were working with not, okay, when you were working with not, you just had one number. Okay, it was something like this. Yeah, you just had not 1, 0, 1, 0, something like that. But in and other cases, and or XOR or right shift, well, not right shift. Right shift is actually different from these three. But yeah, let's talk about and or and XOR. Well, they have this type of idea. You need two numbers. Okay, you need two numbers. So let's try some example questions. Let's say we have 1101 and 1010. Well, the output will be 1 into 1 is 1, 1 into 0 is 0, 0 into 1 is 0, 0 into 1 is 0. So the output will be 1 0 0 0. Okay, let's say we have something like 1 0 1 0 1 1 0 0 and 1 0 1 0 1 1 1 1. What will be the output? Well, 1 into 1 will be 1, 0 into 0 will be 0, 1 into 1 will be 1, 0 into 0 will be 0, 1 into 1 is 1, 1 into 1 is 1. Since we have zeros here, both are zeros, definitely whether here we have 1 or 0, it doesn't matter. We can short circuit this. Okay, we can short circuit this. So 0 0 will be the output. Okay, because we know if you have 0 in one input, okay, you need two inputs. If you have 0 in one input, that means the output is going to be definitely 0 for that specific number place. Okay, so keep that in mind. So what about decimals? Okay, what about decimals? Well, in decimals, they will mention the type of system they are using. Let's say if they are using 2's complement 4-bit system. Yeah, let's say they're using 2's complement 4-bit system. And let's say we have to find the answer for 6 and -4. What will be the answer? Well, first of all, we have to convert 6. Well, 6 is equals to, since it's a positive number, the first bit will be 0. 6 can be represented as 1 1 0. And for -4, okay, first of all, let's find out 4. 4 will be equals to 0 1 0 0. Since we have to find the negative, first of all, we have to find the ones complement, which is 1 0 1 1. And then we have to add 1 to this. If you add 1 to this, you will get 1 1 0 0. Why? 1 plus 1 is 1 0. So you get a 1 here. 1 plus 1 is 1 0. So you put a 0 and here 1 here. And it will be 1 1 0 0. So -4 is equals to 1 1 0 0. Which means the output will be 0 0 1 0. What's the answer then? Since this is equals to 0 1 0 0, it's a positive number. Okay, and 1 0 0 means it's 4. So the output will be positive 4. Okay, so that's all you have to do. You just have to convert it to the system they are represented, okay, in binary, and then do the operation. That's it. Straightforward. Very straightforward. Let's say we have 2's complement 8-bit system. Okay, and they're asking us to find 100 and 101. What's the output? That's the question. Yeah. So let's try this. So 100 can be given as, since it's a positive number, the first bit will be 0, 64, 96, no 16, no 8, that is a 4, no 2, no 1. What about 101? Well, that will be 0, 1, 1, 0, 0, 1, 0, 1. So 100 and 101 will be equals to 0, 1, 1, 0, 0, 1, 0, 0. So that's actually 100. So the output will be 100. Okay. So this is how you have to do AND operation. You have to do AND operation. Now let's talk about OR operation. OR, bitwise OR. Well, it also needs two inputs like AND. Okay, like AND. It also needs two inputs, which means four rows. Yeah, four combinations, you may say. Okay, so let's say we have the inputs A and B. A, B. OR is given as A plus B. Okay, so it will be 0 1 0 1 and then 1 1 1 1. Sorry, 0 0 1 1. Okay, so it will be 0 0 1 1. So what do we have here? 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is equals to 2. I know, but we can't put 2 here, we have to put 1 here. Okay, so the idea of OR is if any one of the inputs is 1, if any one of the inputs is 1, the output shall be 1. Okay, so that's the idea. So let's say we have 1 0 1 0 or 1 1 0 1. What will be the output? Well, first of all, write them down 1 0 1 0 1 1 0 1. So what you have to do here is just check if one of them is 1. Okay, 0 1 1 0 1 1 0 1 1. Since both are 1 here, it doesn't matter. The minimum requirement for the output to be 1 is any one of them is 1. Okay, any one of them is 1. If both are 1, great. That's also 1 because one of them is 1, right? So the output will be 1111. Okay. What about decimal? It's the same story. Okay. Let's say we have 6 or -7. Okay. They are saying this uses 4 bits 2's complement. So 6 can be given as 0110. 7 can be given as 0111. -7 is the equation. So we have to convert it 1000 and 1001. We are adding 1 to this. So -7 will be equals to 1001. Yeah, 1001. What should we do now? Well, since we are doing OR, we have to check if one of them is 1, it's enough. Okay. I mean, I'm not saying one of them has to be 1. Okay. I'm saying one of them is 1, that's enough. Okay. So the output will be 0 and 1 means 1, 1 and 0 means 1, 1 and 0 means 1, 1 and 0 means 1. Okay. Well, this is a problem. You can't write this down directly as, 1, 2, 3, 7, and 15. No, you can't write them down because the problem is it's a 2's complement form. Okay, 2's complement form using 4 bits. Okay, so you can't write this down directly. You have to first convert it to the number because this means if the first bit is 1, that means it's a negative number. So you have to find which number this is. So let's do that. So first of all, converting it back to, the 1's complement. Then we have to add 1 to this. So it will be 0001, which means this is the positive 1. Positive 1. So which means this is equals to -1. So 6 or -7 is equals to -1. Okay, in 4 bits 2's complement system. Okay, what about 8 bits? Let's do a question in that too. Let's say we have 47 or -93. Okay, how do we do this? Well, 47 can be given as 0. I'll write that down. 0, no 64, that is 32, that is no 16, but there are other 4 bits. What about 93? 93 is equals to 0 because it's a positive number. This is -93, I know, but we have to start from positive number in 2's complement. 0, 64, that is no 32, that is a 16, 80, and 88, 92, 93. Okay, so we have to find 1's complement first. Okay, and then we have to add 1 to this, so it will be 101 00011. So -93 is equals to 101 00011. So what will be the output? 1 and 1 1 1 and 1 1 1, oh sorry, sorry, not and, 1011 1011 101 1001 1001 0 0 or 0 0. 1 or 1 is 1, 0 or 0 is 0, 0 or 1 is 1. Okay, you can't directly write this down. Why? The first bit is negative. It's 1, which means the number is negative. So you have to first of all find the 1's complement. So 0, 1, 0, 1, 0, 0, 0, 0. Add 1 to this, so it will be 0, 1, 0, 1, 0, 0, 0, 1. So what is it? 64, 80, 81. So this is equals to 81, which means this is equals to -81. So 47 or -93 bitwise operation is -81. Okay, the output is -81. Cool? Yes. Now let's talk about XOR. Okay, now let's talk about XOR. What is XOR? Well, it also needs four uh, four rows. Okay, 4 combinations, which means we need 2 bits. Okay, so let me draw them down. So we have A, B. XOR actually has a symbol like A XOR B. Okay, it's not exactly a dot. It's not exactly a positive symbol. Okay, the positive sign. It's combination of both. Okay, so 0 1 0 1 0 0 1 1. Okay, so what the idea here is, if any of them is 1, okay, if one of them, okay, if one of them is 1, you can put 1 here. Since both are 0, it's 0. Since one of them is 1, it's 1. Since one of them is 1, it's 1. Since both of them are 1, you can't put 1 here. You have to put 0 here. That's the idea. Pretty straightforward. There is nothing more to it. Okay. One of them only has to be 1. Okay. To be the output to be 1. Okay. The output to be 1. One of the input can only be 1. Okay. One of the output can only be 1. That's the idea here. So let's say we have 1010 XOR, okay, 1100. What will be the output? Well, write that down in a vertical format first so that you can do it easily. So 000 10, there is only one here, so there is only one here, so it's 1. 0 XOR 1, well, it will be 1. 1 XOR 1, it will be 0. So the output is 0110. Okay, so let's do with normal ideas like 4 bits 2's complement and all. So let's say we have file XOR, and let's say we have -2. Yeah, it's better. So file is equals to 0101. 2 is equals to 0010. So 1's complement is 1101, and -2 will be 1110. So -2 can be given as 1110. What will be the output? 1 XOR 0, 1. 0 XOR 1, 1. 1 XOR 1, 0. 0 XOR 1, 1. So what is the answer? Well, first of all, it's converted. So it will be 0100, adding 1 to this 0101. Well, that is equals to +5, which means this is equals to -5. So what will be the answer for 5 XOR -2? Well, it will be -5 if we are using 4 bits 2's complement. Okay, 4 bits 2's complement. Now let's talk for 8 bits. Okay, let's say we have 100 XOR -3. Well, -3 can also be represented by using 8 bits, right? Yeah, why not try that? So 100 is equals to 0, 1, 1, 0, 0, 1, 0, 0. 3 is equals to 0, 0, 0, 0, 0, 0, 1, 1. So 1, 0, sorry, 1, 1, 1, 1, 1, 1, 0, 0, and add 1, 1, 1, 1, 1, 1, 1, 0, 1. So this is equals to -3. Let's write that down here. 1, 1, 1, 1, 1, 1, 0, 1. So what will be the output? 0 XOR 1, 1. 0 XOR 0, 0. 1 XOR 1, 0. 0 XOR 1, 1. 0 XOR 1, again 1. 1 XOR 1, 0. 1 XOR 1, again 0. 0 XOR 1, 1. Okay, so let's convert it. 0, 1, 1, 0, 0, 1, 1, 0. Adding 1 to this, it will be 0, 1, 1, 0, 0, 1, 1, 1. Okay, so what is this number? 64, 96, 100, 102, 103. Okay, so 100 XOR -3 is equals to -103. Why is it -103? Because this is -103. Okay, so these are the basic bitwise operations. Okay, now we have to talk about the right shift and then the left shift. Okay, bitwise operation. Let's say you have a number like, well, first of all, let's talk about right shift. Okay, let's talk about right shift. What happens when we do right shift? Okay, that's what we have to talk first. So how does right shift work? Well, first of all, I'll introduce you the operation. So this is the right shift. Okay, let's say you have a number like 100. Okay, and they are saying shift it by 1 bit. Okay, 1 place. Okay, what this means is, since 100 can be given like this, okay, it has a position value here, place value here, and place value here. You're shifting the bits, okay, in this direction by 1 place. Okay, so what happens is, okay, you are moving the number past this fixed point. Okay, past this fixed point. So what happens is, this number becomes 10.0. Okay, and thing is, the numbers after this point will be discarded. Okay, so the final answer will be 1, 0. So for this question, the answer will be 1, 0. So what about if you have something like 1101? What will be the output? Well, the output will be 110. Why? You are moving in this direction. Okay, you are moving the number in this direction, and you are moving it by 1 place. So the point is here. Since you are moving the number, okay, it becomes 110.1. And we know this one is discarded. So finally we have 110. Okay, what about this number 1011 moved by 3 places? What happens there? Well, the last 3 bits will be discarded. That's how it's going to happen. So the output will be 1. Okay, so here you have the point. Okay, so you're moving 3 numbers in this direction. So it will be 1.011. Well, then you're discarding these 3 bits, which means the output will be 1. Okay, so what about something like 11010011 and you're moving by 5 bits? Okay, just discard the last 5 bits. That's all. So the answer will be 110. That's it. Okay, so this is how you can do right shift. So what about if we have decimal numbers, decimal number system numbers, something like 73? Okay, you're moving it by 3 bits. What you have to do is, first of all, convert it to binary. It's easy. Just discard the last 3 numbers. That's all right. Yeah. So how can you do this? Well, 73 is equals to 64. Okay. No 32, no 16. That is 8. Yeah. 72. No 4, no 2, no 1. And you're moving by 3 bits, which means you're discarding last 3 bits. So the answer will be 1001. So what is the answer here? Well, one is this is given as 1, 2, 4, 8, 9. So this is equals to 9. Okay, 73, right shift 3 by 3 place value. It will be 9. Okay, what about something like 200? Shifted by 4 bits. So first of all, convert 200 into, binary. So 128, 192, there is no 36, sorry, there is no 32, there is no 16, there is an 8, which means completes 200, no 4, no 2, no 1. And you're discarding last 4 bits. So the output will be 1100, which means well, 4, that is equals to 1100. So the answer will be 8 and 4, 12. So 200 right shift 4 bits is equals to 12. So this is how you have to do right shift. Left shift. What happens when you do left shift? Okay. So the symbol is like this, the opposite. Instead of discarding, we just had zeros, extra zeros, which means we are just moving in the left direction. Okay, we are moving in the opposite direction. That's the idea. So something like this, 110, and let's say you're moving in this direction by 1. What happens is 110 point is there, and you're moving in this direction by 1 place. Okay, so what happens is 110 0 point will be given. Why? Here there is an imaginary zero, right? Yeah, we can consider there is an imaginary zero. So when you move the number by 1 place value in this direction, it becomes 1100. So the answer will be 1100. Or you can think like right shift means delete a number, left shift means insert a zero. Okay, that's it. So let's say we have something like 11010011, and let's say we are doing 3. Okay, yeah, left shifting by 3. What will be the answer? 1101001100. That's it. Okay. So what happens when right shift is done? Well, when you are doing right shift, the number becomes smaller. When you're doing left shift, the number becomes bigger. Okay. I know when you're cooperating with right and left, right is normally considered as positive. Okay, which means it should be bigger. Yeah. But in this case, it's a little bit opposite. Okay. Keep that in mind. Now let's do with decimal numbers. Okay, I'm just going to do with small numbers because if we do something like a big number, it's going to hurt. It's going to hurt. Okay, so let's say we have 7 and we are doing left shift by 3. Okay, so which means first of all, write it down in binary. Okay, and then add 3 zeros, right? 111000. Okay, now we convert it back to decimal. So it will be 1, 2, 4, 6, 8, 8, 16, 24, 24 plus 32, 56. So 7 left shift 3 bits is equals to 56 to the base 10. Okay. And what about if you have something like, I don't know, 19 shift by 4? What will the answer? Well, 19 is 16, no 8, no 4, 2, and 1. Adding 4 zeros after this, 1, 0, 0, 1, 1, 0, 0, 0, 0. What will be the answer? 1, 2, 4, 8, 16. 16 plus 32, 48. Okay. 64, 128, 256. So 48 plus 256, 304. Okay. So this is all you have to keep in mind when you're doing bitwise operations. There are also NOR, well, first of all, NAND, okay, then NOR, then we have XNOR, okay. Um, Read about these stuff, okay, these are not that much important here, but when we go to logic gates, they will become very important. So for now, just keep them in mind, okay, these things in mind, and that's enough for now, okay. And this series ends now with the 20th video, and let's meet in a new playlist where I talk about logic gates.
Thanks for watching the 20th and final video in our number system series. If you found this tutorial on bitwise operations helpful, don't forget to like, share and subscribe for more lessons. Hit the bell icon to stay updated with our latest videos, check out the full playlist to master number systems, and follow us on social. I'll see you in the next video. Until then, keep learning and stay curious. Bye bye.